for it.
All right, thanks everyone for attending this month's Ask an Expert session. This month's session will be about timing closure. So anything timing closure related is good. Steve, introduce me, please.
So welcome everybody. Our expert today is Steve Elzinga. Steve has been in our FPGA training group for over 6 years, taught many different classes. Prior to that, he was working in video processing cores and FPGAs, and he started as an applications engineer. He focuses mostly on timing closure these days, but he is well versed in many different subjects and teaches many different classes along with me. I will introduce myself shortly. If you need to reach him, his email address is there, very easy to remember. So Steve, with that, take it away.
All right, thank you, Steve. Just some housekeeping items. If you wouldn't mind keeping yourselves on mute, that way we can minimize any background noise. If you do need to ask a question, just feel free to unmute yourself and ask the question. So that's not a problem. We do have videos, what we call quick videos. These quick videos are roughly 5 minutes in length, and so they cover a very specific topic, something that should be able to be explained, hopefully in a very concise manner in 5 minutes. Quick videos. So we have those up on YouTube. You could do a quick search on YouTube, Intel FPGA, and a lot of Intel FPGA training materials will come up at that time. So ground rules, like I mentioned before, if you wouldn't mind keeping yourselves on mute, that'd be great. That way we minimize any background noise. If you do have a question, feel free to unmute yourself to ask the question, or go ahead and ask the question in the chat window. So either way is fine. Steve Strell, he'll be moderating today. He'll be looking at the chat window for questions. That way I could focus what's being presented on the screen. So he'll keep that running. Let's see. So any questions about timing closure? Fair game. I will do my best to answer the question. If I don't know the answer specifically, I will do my best guess. Based off my years of experience, hopefully my guess will be correct, but more than likely what I'll do is jot the question down with a follow-up later about that. For that matter, questions about FPGAs in general, it's not a problem for me either. Let's see. But if the question gets a little bit too involved about a project, I'm happy to indulge questions about projects. But if I see that it ends up getting a little bit too involved, I may defer you to your local FAE there, but again, don't hesitate to ask. We can see the question leads us. All right, Steve, do you want to talk about this slide here?
Yes. So I'm Steve S. Just to make everything more confusing, you got two Steves today. I am your moderator. If you want to ask a question, you can easily unmute using the button at the top of Teams, or you can put and to speak, of course, or you can put something in the chat. I will be constantly monitoring the chat and relaying questions to Steve as they come up. So please get your questions in. We'd love to have a big queue of questions that I could ask Steve. And so Steve's going to do a little intro and some other, show you some new stuff with timing closure right now. But let's get those questions in and going. All right, Steve, go to it.
All right, thanks, Steve. So timing closure can be a challenging aspect of the FPGA design process. Just when you think things are going your way, you're almost done. Something happens along the timing closure path, and one of your paths is failing timing. So when we mean by timing closure, what we're talking about is iterating on your FPGA design so that all of your paths are constrained and all of your paths pass timing. So that way, that your design will work as expected inside the FPGA. So that's what we mean by timing closure. Again, all of your paths have timing constraints on them, and all of the paths are passing timing. So in other words, you're doing a timing analysis on those paths. That's what timing closure is about. So hopefully with this Ask an Expert session, we can indulge in some questions there that you all may have had with the timing closure issues. We also offer classes on timing closure. So if you feel like that this session didn't quite cover what it was that you're expecting, look at our class list that we offer. that we publicly offer. Sign up for the time enclosure class. We go to more details about the different aspects of the tools to help with time enclosure. One of the things that I did want to talk a little bit about, kind of to prime the pump, so to speak, is we have a new database that's inside of Cordis. Let's see, that was made production in version 23.3 of Cordis, if I remember correctly. This is it's called the DNI database. Not that you need to know this. It stands for Design Netless Infrastructure. The engineers here at Intel, did a lot of great work to make this new database, and it's supposed to be seamless to the customers. Customers aren't supposed to notice anything. Now, given that it's a new database, there might be some quirks that pop up from time to time. Hopefully not. But it's supposed to be seamless to the customer. So the customers really aren't supposed to notice that there's a new database in there. But with this new database, there are some features that we're able to incorporate into Cordis. And so one of these features I'm going to talk about is it's SDC on RTL. Let's see. Let me talk a little bit. I just realized. Let me talk a little bit to these bullet points. I didn't address the bullet points that I have there on the slide. So with this
Steve,
new database,
before you get into
yes.
that, we actually already have a question in the chat. So
oh, fantastic. Yes.
Yeah. So this person has an external clock pin that's driving some logic that's easy to constrain for them. The clock is used by some registered divider logic. How would you constrain the new clock generated by the registered divide using your .sdc file?
Let's see. Okay, I do see it in the chat window. Give me a second here. I'm going to read it again just so I make sure I appreciate the question. Okay, this clock is used by registered divider logic. How would you constrain the new clock? Oh, okay, yes. So there is a create generated clock SDC command. So that's the command I would use. With the create generated SDC command, what you do, one of the parameters that you pass into this is the source, and in this case would be the clock coming into your clock divider logic, and then the target would be the output of this logic. So anyway, the create generated clock command is the command that you'd use for any internally generated clock that you have. I believe that's what the question was about.
Yeah, I think a basic create generated clock command would do the trick for that. So yeah.
Yeah, that's what it sounds like. Fantastic. Yep. Okay, thanks for the question.
All right. No others right now.
Okay. Let's see. With the okay, so that's right. So with the new database, there is going to be a Cordis Pro 2.0. Like I said, we just incorporated the database, became production in Cordis version 23.3. So we have that. Because of this new database, there are some features that we're able to get into Cordis. No loss in functionality. So in other words, it's supposed to be seamless to the customers. You're not supposed to notice anything except for these new features that come along. And like I said, maybe some quirks that came up, which I want to say is expected, but it should be expected. But with anything new, stuff like that does happen. And of course, with the new database, we want to focus on efficiency and productivity. Okay, so SDC on RTL is a way that you so previously with the SDC commands that we have, and so SDC, for those of you who may not be familiar, stands for Synopsys Design Constraints. Is the de facto industry standard that everybody in digital logic uses to timing constrain their design. Now, again, when I say timing constrain your design, you need to tell the tools how long you expect a path to take, and then the tools will run the place and route for the paths in your design with that constraint in mind. So when I say timing constraint, that's what I'm referring to. SDC is a means of, again, it's the de facto industry standard. SDC is a means to tell the tools the timing constraints that you have for your design. So now, Steve, with this, yes, Steve, go ahead.
We got a couple more questions coming in. Let me summarize this one for you. Somebody's asking about constraining high-speed transceivers when using the custom or basic mode. And let's see, is there multiple questions there? Is there a way to make platform designer provide SDC constraints based on the parameters? I think they're so they're asking about constraining the transceivers. and that's an IP. So I would think that that's, SDC is automatically created when you parameterize that, right?
Yes. The if I recall, the transceivers, and I'd have to double check with this. So our transceivers are used in any high-speed serial communication, such as Ethernet or PCIe or something like that. And I believe, and I'd actually have to double check this, but I believe the transceivers, even the transceivers that you create that don't, where you're not interested in a specific protocol, where you want to, roll your own. I believe those transceivers come with their own SDC constraints as well. So the need or the worry to have to constrain those transceivers that you are utilizing should you shouldn't have to worry about that. However, having said that, we did have an old iteration of our timing analysis class where we actually went through the process of here's how you constrain the transceivers. But we got rid of we got rid of that section years ago because the transceivers were constrained by themselves. So with this kind of wordy preamble that I'm getting on here is I am out of practice on knowing how to constrain transceivers, so I might have to defer to that.
I think
We
it's
might have
I think mostly, like you said, that it should be automatically constrained by when you add it as an IP. But
yes.
again, it depends on the device, I think, and the IP that they're using. They just say high-speed transceivers in the question, so I don't know what IP they're using or what.
Yeah. The what I was wondering is if we had an online version of that old version of the class where I could refer them to, as far as constraining is concerned. With this particular question, I'm going to have to hold off for now and do just a little bit more research with that just to verify that. But like I said, I'm pretty confident that regardless of the transceiver type that you're
Oh,
instantiating, it should come with its own SDC file.
so the person is asking that, saying it's not IP, they're creating a custom interface. If the SDC file is generated, where would I find it? Ugh, I'm not so
Yeah,
sure about that
so
one
custom
either.
interface. So yeah, so even with that, it's a custom interface. So in other words, you're not using Ethernet or PCIe or anything like that. You're instantiating the transceiver, but I'm guessing that you're not instantiating the primitive. If you're instantiating the primitive, then yeah, you'd have to write your own SDC. But if you're not instantiating the primitive, so for example, you just going in and instantiating the F tile or E tile or something like that, it'd be basic, and you're doing your own custom interface. Even with that, there is an IP creation that you are doing, and with that IP creation, there should be an SDC file associated with that because constraining transceivers for the particular transceiver that you are using is a known quantity. And as such, to help our customers along, we go through and automatically create those SDC files. So I get it that you're not using a standard protocol, you're rolling your own. You just want the high speed capabilities of the transceivers to communicate chip to chip for whatever it is that you see. And even in that case, I believe the SDC file should still be automatically created.
Yeah, he can't find the file, so I guess that's the difficulty
mm,
here.
okay, all
So
right, yes. So I will have to follow up on that. That's an excellent question. Let me follow up on that and about constraining transceivers and the fact that that SDC file is not there. So I'm just gonna have to do a little bit more research
yeah,
into that.
I'll take note of the person who's asking the question, and we can get back to them.
Okay, thank you.
Yep. There is another question in the chat, um, referring to asking about DNI. Are there any reference documents to know what DNI actually does in terms of netlist reuse, functions to access and clear the database, which gets huge? Any netlist reuse between different compiles? So
That's your question is timely. This actually came across my desk about a week ago, saying that the database gets huge, and the engineers here at Intel are aware um, of this. And I actually ran into this. I suspect I ran into this problem, and coincidentally enough, is when I was trying to create a transceiver design, I kept getting these odd error messages. And that's why I said, quirks come up. And this was a particular quirk I came across, and I had no idea what the error message was referring to. When I cleaned out my DNA database, that error message went away, and things were good, but it was frustrating nonetheless. The As far as commands are concerned, if you give me just a moment here, I can actually type in a tickle command. That there's going to be a knowledge database article talking about this, and you can let's see. I'm going to just type it in the chat window here. There's a command that you can use in tickle if
Is
you're
this something
automating
new,
your
Steve?
flow.
That's not in.
This yes, it is. It's not documented. A knowledge database article is going to be created. There is the tickle command there. Delete stale sandboxes. So if you feel like if you see from time to time that this DNI database is becoming unwieldy, if you've automated your flow, go ahead and use that command. Otherwise, it's a manual process of well, either way, it's a manual process, right? You have to add the command manually, or you have to go in there and delete it yourself. Like I said, the engineers here at Intel are aware of that. I don't know what a fix is going to come in for that.
Related question, they're asking about DNI specific documentation.
So there isn't DNI specific documentation in the Tickle API documents that we have. You can see the functions that are related to DNI, and of course, if you need to use one of those Tickle functions, just prefix it with DNI : : I typed that in the chat window there. But yeah, just looking in the Tickle API documents that we have.
I think I just found it in the Cordis help. I can put that in the chat for you.
Perfect. Okay, thank you, Steve. So that's what we'd have documented. But like I said, the DNI database is supposed to be seamless to our customers. And you just heard me talk about a couple of the quirks that were there in DNI. So as such, there are features that result that come across as a result of the DNI being implemented. And one of those features is the SDC and RTL. Another feature is how we have multiple type of RTL viewers inside of Cordis now. That's a result of DNI. Another result is being able to do we call it early timing analysis, where you can do timing analysis on your synthesized design. So these are the types of features that came as a result of the new DNI database. And so you wouldn't know that those features came across as DNI unless taking a class or something like that. Because like I said, a new database is supposed to be seamless to the customer. The customers aren't supposed to notice anything except for these features. And then of course with the Tickle API functions that we have now.
I just put the link in the chat for you.
Okay, thank you very much.
Another related question to DNI, very popular today. Does it reuse netlist between compiles?
Oh, let's see. So that's a loaded question. Let's see where to begin with that. So there's something there's a feature that we have inside of Cordis called the block-based incremental compilation that can reuse netlist, but you set aside specifically netlist for specific regions of your design to be reused. So there's that. So that's a feature that we had. That's a feature that currently exists. When it comes to synthesis, synthesis has always been reused. And so once you've synthesized your design, the fitter is the place and route engine of Cordis, the fitter would always reuse the synthesized netlist as well. So there are instances where the netlist gets reused, but it's purposeful. So in other words, it's something that you have to go in and do yourself. And so it's not necessarily a feature of DNI that netlist gets reused, but it's something that Cordis has had the capability of doing for a long time. Yeah. So not DNI specifically related, but is something that Cordis could do currently.
Okay, I think we're good on questions right now.
All right, thanks for the questions, everyone. Let's see here. Okay, SDC and RTL. Okay, let's see. I talked about SDC. Yes. Okay. So with SDC now, with the DNI, we're able to target HDL objects now with SDC constraints. And so he thinks like, well, what's wrong with the SDC that I'm doing currently? Nothing wrong with what you're doing currently. What you're doing currently, what that means is that you at least have to have a net list of source before you attach your SDC commands to your design. So in other words, you have to have something that's been at least analyzed and elaborated as far as synthesis is concerned, because the SDC has to be able to find an object inside there. With the SDC on RTL, you don't have to wait for that. You can do it immediately on the RTL, attach the SDC commands to objects inside of the RTL here. And with this SDC on RTL, here we have, even though it's an RTL view of the HDL that we have, the idea here is that with the SDC commands that we have, we are targeting the RTL names. So U0, that is the instance that we have there. Clock in is a port into that instance. So here we're targeting we're creating a clock period based off of an RTL name called clock in. And oh, you know what? I thought I had turned those timings off when I created these slides. Sorry about that. And here's the command. So going back to the create generated clock. So if you create a clock provider,
perfect
perfect
slide
example
for what was asked earlier.
Yes. So this is the command right there highlighted, create generated clock. And what you do it is we have the source, and that is the input to the clock divider. And then we have the target, which is right here, and that is the output. Here's the clock divider. That is the output of the clock divider, and targeting specifically the pin on clock div. And so, admittedly, with this, we see that we are going down hierarchically to the object that we want to attach it to. And admittedly, you have to understand, in this case, you have to understand a little bit about the synthesis process. You have to understand that this would create a register. And if a register is created, then you'd have to understand that Q would be a pin on that register. So admittedly, there's a little bit of knowledge of what's going on under the hood, but mostly you can just target RTL names inside there. Let's see, you know what? I take that back. Let's see, clock div. No, sorry, I was wrong with that. Q end up just being an object inside of the clock divider. I take that back. Having the same name as the pin name tripped me up a little bit there. Okay, and then another example here with the set faults path. Again, targeting the port name of the instance U0. We have that async reset. And then notice here that in order to target objects in the RTL, we preface it with the DNI : : let's see. I believe. Oh yes. Excuse me. Just other examples of targeting here. If you want to target nets, we go ahead and use the collection command get nets, and we target a net name that exists inside of HDL, so the signals that you've created. Now, one thing with the SDC on RTL, it is SDC 2.1 compliant. What that means, part of what that means is that with the SDC on RTL that we have inside of course, we do not bring in the extended SDC commands that Intel has added. Some of those extended commands are the get keepers collections and the get registers collections. These are Intel extensions. They are not part of the original SDC specification. So we cannot use these collections when doing SDC on RTL. And for that matter, any SDC extended commands you can't use when doing SDC on RTL. Let's see. So viewing the constraints that you've placed on inside there. We can view the constraints inside of the RTL analyzer, and let's see, I've got Quartus up. Hopefully I can, yes. So there we go. So clicking on this RTL viewer right here, so notice that we've got 4 different RTL viewers. Clicking on the third one there will generate reports for you, letting you know if the SDC constraints that you added on there took appropriately or not. So that is what we're seeing here with that third RTL analyzer view. We can take a look at the constraints that we've added. And with that, I mentioned a little bit about the post-synthesis static timing analyzer. With the SDC on RTL, it allows you to do timing analysis on your design after synthesis, and this is handy because instead of going through the entire place and route process, or even the beginning of the place and route process, you can see if all of your SDC commands have been applied to your design. That way you can, without even starting the fitter, you can make sure that your SDC commands are good by doing early timing analysis. And here, go through just showing the different diagnostic reports that you can run inside a time analyzer to make sure that your SDC commands are good. And so that was a little bit of the intro that I wanted to bring up, talking a little bit about DNI. I did mention at the beginning of this class that we do have a time enclosure class. It's a 2-day class. Well, it's a class split into 2 days. You don't have to register for both days. There's the first day is the lecture, the second day is the workshop. And so if you're interested in more time enclosure issues, feel free to sign up for that. All right, so that was the end of my little presentation there. Are there any other questions in the chat, Steve?
Not right now, but I've got some questions that were submitted ahead of time, so I'm going to bring those up. Of course, if anyone does have any questions, please feel free to post or unmute yourself, and we will do what we can. So let's see. What's the best way to manage high fan out?
Okay, so best way to manage high fan out. So let me I've got a bunch of presentations open. So let me there we go. Let me pull up one here. Bring it into view. So in this, I bring this class in. This is from the time enclosure class. Resize.
And I'm going to actually check when we next have our full time enclosure class in our schedule, because I was going to let people know if they wanted to sign up for that. But while you're doing that.
Okay, thank you. All right, let's see. Actually, let me get out of presentation. Oh, where to go? Sorry, give me just a moment here. Okay. Okay. So okay, so with high fan out might not necessarily be a problem. There is a tool inside of Quartus called it's called Design Assistant, and what Design Assistant does is it looks at your design. It gives you recommendations on what you can do to potentially improve your design. Part of the reports that Design Assistant can give you is high fan out. Now, you don't necessarily know if high fan out is going to be a problem or not. However, you will know if it's going to be a problem if you've got some paths that are failing on that particular high fan out net. So looking at the Design Assist report can help you lead you in that direction. And let's say the question was specifically what's the best way to manage it. There's a number of ways to manage it, and I wouldn't necessarily say that there is particularly a best way. Okay, that particular high fan out net. This is what it was. It ended up being a reset net that I go into more detail in the class. Sorry, give me a moment here. Hopefully, I can. There we go. Okay, so what are the ways that you can manage fan out? Is through an assignment called max fan out. If you look, the tools automatically have a threshold as far as fan out is concerned. And if it goes over that threshold, then it starts automatically replicating logic inside your design. I don't know what that threshold is, but if you see that for whatever reason that threshold isn't where you expect it to be, you go ahead and place this assignment on the particular node that you're interested in and assign, whatever the maximum fan out of that node should be. When it reaches that threshold, what the tools will do is they'll automatically start replicating logic to accommodate that. And you might think it's like, well, what's the issue with the fan out? A potential problem with the fan out is, let me give you this big scary high fan out net that we looked at. The potential issue is here, so you can kind of
go full screen, Steve, with the presentation, just to make it a little easier for folks to see.
Yes. Yep. Thank you. Right. So as you can see here, potential source of this high fan out is probably about right here. Now you can imagine this is just looking at the vectors coming in to where this is at. Sometimes people refer to this as a black hole or something like that. It kind of looks like it's things want to kind of circle and congregate around this area right here, you could imagine right here. So imagine the signal right here doesn't have far to travel going from here, but it can from here. If we were to replicate logic inside there, what we do, let's say we replicate it 10 times. Now we've got the single source going into whatever research circuitry that we have, but that reset circuitry is replicated 10 times. Now at least we can spread out, we can more balance the timing delay that would happen as a result of this high fan out, and thereby this particular net right there would potentially be starting right here rather than right here. So that's why it's important to recognize the high fan out. And again, the whoops, missed the. There we go. So that's why you want to control your high fan out. So again, let's get back to how do we control our high fan out. So here's this this max fan out assignment that you can utilize. Oops, that's not what I wanted. There we go. We can also do there's a duplicate register assignment that you could put inside of your design. What you tell the tools is that I want to have more control over duplicated logic. Now I mentioned that the tools will automatically duplicate logic. There might be a reason why you want to duplicate the register yourself. And so this particular assignment that Quartus takes, and these assignments, when I talk about these assignments can be found in the QSF file, the Quartus settings file. Here we have a register that we want to duplicate or replicate, I should say. We want to replicate it 50 times. So here we have the name called reg, and we want to replicate it 50 times. So that's what we have here. The assignment would go as follows: duplicate register -2, and then the instance name that we have that we're targeting. In this case, the instance name is reg, and then the number of times you want that replicated. And here you just put the number 50 inside there. So that'd be another way that you could manage high fan out. There is another assignment that's called duplicate hierarchy depth. This way you can go ahead and manage replication of logic hierarchically. And how this assignment works is you have the assignment name, and again, this is found in the QSF file. We have the the last reg name, and so here we have a bunch of registers that we put inside of our design to pipeline. This is the last reg name, so we'd have reg z inside here. And then the number is how many times, how many levels of hierarchy you want these registers replicated and pushed down into. And so here's the original circuit. After we apply the assignment, this is how all the registers get pushed down hierarchically and replicated.
So Steve, it looks like there's a number of different strategies for high fan out. Do you have a recommended one? What works best, or what you would recommend in most cases?
Okay,
would it be manual duplication, or is it really situation specific?
I think it's situation specific. I'm going to say the best one is the one that works best for the situation that you currently find yourself in, and
okay.
whichever one that you find easier to manage yourself. I believe all of these work equally well. If you find it easier to imagine, replicating registers, you can do that. Now, again, we're targeting just a specific register in this case. With the max fan out, when the tools reach that threshold, it could be replicating lookup tables or something like that, which would be harder to do yourself. There is the duplicate hierarchy depth. Talked a little about that. So if you understand what that does, you might find yourself in a situation to use this. And there's a manual duplication too, if you want to go down that route. And when I say go down that route, there's nothing wrong with this one either. It just takes a little bit more HDL coding. Here we have an example of VHDL. So what we're doing inside here is we're putting we are replicating the logic inside of the HDL, and then we're putting attributes inside there so that the tools will not optimize them away, combine like logic and stuff like that. Here we have the VHDL example and then Verilog example. Okay. So those are the methods as far as managing your max fan outs. And like I said, the managing the max fan outs, in my opinion, really is situational. If you understand what you have available to you, then I think you'd be able to adjust what it is that you need for your design.
Sounds good. Yeah, as I put in the chat, you do have a session of the timing closure class being taught next week, February 15th through 16th. So
Oh,
you can
good.
see
Okay.
this, and people can get more details if they can attend that. So we got some other
Perfect.
questions coming up in the chat. Are there any plans to allow timing constraints to be embedded in the RTL via VHDL attributes?
The yes, so that via VHDL attributes.
VHDL attributes.
Yes, the not that I'm aware of.
Okay.
Um, yes, I have not heard any discussions about embedding timing constraints via VHDL attributes or Verilog attributes for that matter, or attributes in general. Only through SDC files is what I'm aware of. Now you can embed other types of assignments, just not SDC style timing constraints.
Okay. Let's see. Another question in the chat. Somebody's using derived PLL clocks to create the clocks from a PLL. The tool generated constraints with source get combs. When you read .sdc file, it fails. I'm using I'm not sure. So it's a question about using derived PLL clocks. It would be helpful to know what device they're targeting, right? Because derived PLL clocks is not needed for many newer devices, right, Steve?
Yes. Let's see. So I am browsing through the question
ARIA
and chat
10. They're
window.
asking about ARIA 10. So I guess you do need
ARIA
derived
10.
PLL clocks for that, right?
Yes, the dash source get comment. Let's see. I'm not familiar with that collection. Get
I think they're saying that that's what they're getting in their as a constraint, maybe when they're using derived PLL clocks. I'm not sure why they'd be getting that. So I'm not sure what's going on there.
the
Version
yeah. I'm not
18.1.
sure. Yeah, I'm not sure what's going on there either. Just as a provide a little bit of context with this question. It's a good question. Drive PLL clocks is a very nice SDC command. I like it. Oriented and older parts. What would you'd use the drive PLL clocks if you instantiate a PLL inside your design. The PLL that's instantiated inside your design, well, I'm just going to refer to it as an IP. You go into Chorus, you create the IP. It's a PLL IP that you've created. It's a known quantity. So in other words, you've put all the parameters in there already, right? And so this PLL is instantiated inside of your design, and you can use the SDC command drive PLL, drive PLL clocks. And what the tools will do is it will analyze the PLL IPs that you have instantiated inside your design, and it will extract all the parameters information, and it will create all of these SDC constraints, all the create generated clocks. So you don't have to worry about that. So it's a very handy handy SDC command to use for ARIA 10 and older. For Stratix 10 and newer parts, you can say that drive PLL clocks is deprecated. It's not going away anytime soon. It's not needed for Stratix 10 because the PLL IPs that that Chorus creates come with their own SDC files. So in other words, the drive PLL clocks is unnecessary for Stratix 10 and newer parts because of the SDC files that are created with these IP that have all of these generated clocks as well. Now, as far as the specific question is concerned, the source get combination. I mean, I'm assuming it's get combinational logic.
I don't think I've ever seen that before.
I haven't seen that either. And so the fact that it's creating something like that is odd. 18.1 is it's getting a little bit long in the tooth. It's been about about 6 years now.
Yeah.
For 18.1. I'd have to say if that was failing at that time, without knowing specifically, I would guess that it is fixed. If that was something that was that constraint was automatically generated using the drive PLL clocks.
That seems odd. Let me see about some other questions here. Some other previously sent questions. Do you want to talk a little bit about Hyperflex? With maybe, so Hyperflex, we've had it in Stratix 10 for years and years now, and now the newer Agilex devices are all going to have Hyperflex, so that's going to be coming to the forefront. Do you want to talk a little bit about Hyperflex in general, or do you want something more specific?
I could talk a little bit about Hyperflex in general. I can kind of circle it back to how it relates to timing and timing closure with
Okay.
with Hyperflex, the you'll hear the traders refer to as a Hyperflex architecture. Well, you hear the Intel FPGA guys refer to the Hyperflex architecture, and what we mean by that is that the architecture inside of Stratix 10 still has your traditional architecture where you've got lookup table register pair combination going on inside there. Then you've got routes going to other lookup table register pairs, and that still exists in Stratix 10. But what we've done, when I say we, I can't take credit for it, but the engineers making the newer FPGAs, what they did back in the time, well, I said newer, it's been a while now, but what they did with Stratix 10 is they decided to add registers in the routing infrastructure inside the Stratix 10. So what we have now, so now not only do we have the LUT register combinations inside of the ALM. ALM stands for Adaptive Logic Module. Not only do we have that inside of the ALMs, but we also have registers inside the routing infrastructure. And so what that means is that we are able to retime. It's an easier way to retime with those FPGAs than it was in FPGAs past. Now, retiming is not something new. It's been around for decades, but retiming is the idea that the tools will look at your design, and to create a balanced delay between synchronous elements, it will move registers through combinational logic. So the tools maintain the functionality of your design. It'll move registers through combinational logic to create a more balanced delay. Now, since we've got registers everywhere in the routing infrastructure, this makes it a little bit more fine-grained. So in other words, instead of going from a register inside of an ALM to another register inside of an ALM, we can now just move that register into a register in the routing infrastructure. We call those registers hyperregisters. So we're able to create a more balanced timing delay. Not only that, it makes it also easier to pipeline designs inside of Stratix 10. So Stratix 10 and any of those newer FPGA architectures that have the Hyperflex architecture has this capability. Now, how this relates to timing is that the with the Hyperflex architecture, the Hyperflex, you have to design when you create your FPGA design, you have to design with the Hyperflex architecture in mind, because the hyperregisters are simple D flip-flops. They do not have any control signals, and so they don't have any clock enables. They don't have any resets. And now the takeaway here is, I'm not telling you to create designs that don't have any resets or clock enables. That's not what I'm saying. So don't come away as like, oh my gosh, those guys at Intel, they don't know anything. But what I am saying is that a lot of times you can get away in your design without using resets or clock enables. So what you do is you have like a valid signal going along. So if you create your design with that in mind, you'll be able to do that. Now, when it comes to timing closure, these hyperregisters end up what's being referred to as a timing endpoint. They end up being a timing endpoint. So if you have a timing endpoint, as far as timing analysis is concerned, is anything where a timing analysis will end. A timing endpoint would be a synchronous element. So I'm talking about like a register or a on-chip memory that we have, or it would be an I/O block. And so the timing analysis ends at the timing endpoints, and then it begins at a timing endpoint as well. These hyperregisters are timing endpoints. What will create a timing endpoint, and what will create a timing endpoint inside of these designs also are if you put timing exceptions inside of your design. Sometimes you have to have timing exceptions. So again, I'm not telling you not to use timing exceptions. Sometimes you have to have them in there. When you put a timing exception inside of your design, that is a timing endpoint. And when you have a timing endpoint for Hyperflex registers, the tools cannot retime past the timing endpoint. So in other words, the tools will retime all the way through the clock domain until it reaches a timing endpoint, and then it will stop at that timing endpoint. Timing endpoints cannot exist inside of hyperregisters. So that's something to be aware of when designing towards Hyperflex registers.
So it goes back to like how you write your code and your use of registers, right,
Yes.
Steve? It's
Yes.
and the tools automatically choose the use of those hyperregisters for you. And if you want to get better performance, better timing performance, you want to remove those roadblocks that you're talking about, the end of the endpoints. If you can remove those limitations, then then the tool can get you even, get you better performance and better usage of the hyper registers.
Yes, that's right. Yep.
Okay. We got another question in the chat. We've got about less than 10 minutes to go, so please get your questions in. Is using set clock groups dash asynchronous still okay? We find it very useful in reducing the large combinations of set false path between clock groups.
Yes. Yes, absolutely okay.
Yes, absolutely.
Yep. The yeah. There's no issues with using that when you have to set false paths. You want to use asynchronous. But I thought it was okay. Well, asynchronous just if the clocks are related, if it's coming out of the PLL, and at the end of the day, I did a little bit of research in that. At the end of the day, it's like, what? It's actually just better to just say all those clocks are asynchronous. Cut those paths, and that way you can go ahead and create your CDC logic without hesitation there. And with having said that, the let me pull up. I'm going to pull up Quartus here. What was new in 23.4? Give me a second here. We do have so this is the HTML editor inside of Quartus. This is the templates button that we have inside of the HTML editor. There is, and hopefully I can find it quickly. Full designs, I think is what I'm after right here. Oh no, I could be able to find it quickly. Oh no, here it is. Parameterizable macros. We do have CDC macros that you can go ahead and instantiate. So what happens is you instantiate these CDC macros. The tools will automatically recognize the CDC macros that you have, and it will create the logic necessary for you with that. Let's see, was there something else? Yeah, okay. I think that's all I wanted to say about that topic there.
Okay. Let's see what else we got. Again, we've got less than 10 minutes left, so please get your questions in. Maybe if there's anybody on the phone who wants to speak up, please feel free. Let me see what other questions I've got here. Over-constraining. Is over-constraining the timing on a design counterproductive?
It can be, depending on how you do it. So a quick, I think a quick and good example of over-constraining is if you have a design that's failing timing, it would be in a particular clock domain, right? There's a path. Let's say I'm just going to say path from register A to register B. That is failing timing right there. If you're to put a set max delay constraint on there, what the set max delay constraint is a timing exception. So what the tools see when you put that timing exception in there, the tools will say it's like, okay, you've got this create clock command on this, you're creating a clock domain here, except for this path from register A to register B, and that exception there is a set max delay constraint. So what happens is that set max delay constraint takes a higher priority. It overrides the create clock command that you have on there, and now you're able to constrain your design in a slightly different way with this set max delay. And so let's say you've got a 10 nanosecond period going on there, and this path from register A to register B is not passing that. You can go ahead and put a set max delay constraint of 9 nanoseconds on that path right there. And since it's constrained a little bit different way, it is a timing exception, and you're over constraining because the original constraint is 10 nanoseconds, and now you have 9 nanoseconds. You have a chance that the tools will honor that constraint right there, in addition to the clock domain constraint that you have as well. There's a caveat. Whenever you change your design, the tools will also place and route things slightly differently. So when you over constrain, that's what's going to happen. The place and route will happen differently. Now, hopefully, everything else will be fine in your design, but there is the potential that you'll end up creating another timing path problem. There's always that potential. So when I say that there's this option there, it's still a good option to do, but also understand that you might end up having to do that in a couple of different places to get your design to get fully constrained. I go into more details, some more techniques on on what to do with something like that in the time and closure class. But just briefly, that would be an example of over constraining. And in my opinion, it's still a good thing to do, but you also have to be aware of the benefits versus what could happen negatively to your design.
Over constraining is usually like a last ditch effort, right, Steve?
Yeah, it's a last ditch effort, but and we say last ditch effort. It's not that it's like something that should be done. It's something that you do when your design is stable or relatively stable, and you are looking for things to do to maybe
And you're
increase the
really
performance or to.
close.
And you're really
Really
close,
close,
exactly.
yeah.
Yes, yes,
You're like on the
yeah,
verge, a few nano or picoseconds even into me timing. So just to get
yes,
that last little bit to get you over the line.
yeah.
Let's see. So we got less than 5 minutes left. I just dropped a survey link in the chat, so I hope people will fill that out. Let's see if there's any other questions before we finish up here. Let's see, something we can do really quick here. Da, 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 da. Okay. Recommended way to constrain clock crossing FIFOs. Is there something special for constraining clock crossing FIFOs, Steve, that you could touch on real quick?
Let's see. The clock domain crossing. So our FIFOs, the FIFO IPs that we generate already have the CDC circuitry inside of there. So the dual clock FIFOs that we have, and they're already automatically constrained. If you're considering, if creating CDC circuitry in your design, gives you, just mild heartburn, it's like, oh, this is so new to me, and you don't want to get things wrong. I'd say it's like, consider using a dual clock FIFO IP that we have inside of course, because that's everything's already automatically happened there. You end up taking a little bit more space, but if you're looking at getting your project done, and you want to be able to do things right, but you're unfamiliar with how to do things properly with CDC, I would recommend using the dual clock FIFO.
And then you're saying it creates its own SDC from the IP.
It does, yes, yeah.
Okay.
Everything's already automatically constrained in the dual clock FIFO for clock domain crossing and everything like that. Yeah.
So you don't need to even add asynchronous clocks or false paths or anything for it.
That's correct. Yep. So with the dual clock FIFO, so you've got a clock that's for the read port and a clock that's for the write port. Inside of the dual clock FIFO, we already have all that CDC stuff worked out, and the time constraints worked out inside of the FIFO. So the dual clock FIFO, you can look as its own self-contained clock domain crossing, where you don't have to worry about what's going on inside there.
Perfect. Okay, we got 1 minute left. Real quick, can you pipeline too much?
I never thought you could, but I was in a meeting once where they talked about, yes, you can't pipeline too much, and that must be totally the exception. And when you pipeline too much, what that means is that you've increased the latency so much where it's just not going from in to out in your FPGA in the time that you want. So in other words, you've got the latency where it just bumps you over the required latency that you have for your design. So in that essence, yeah, you can't pipeline too much. I think also they're talking about it could potentially add unnecessary congestion, but like I said, I think these are really the exceptions, and I've never run across that problem myself. Of course, you do need to be aware of the latency of your design when you do pipeline.
Match latencies everywhere else.
Yes, exactly. Yeah.
Yeah. Okay. All right, Steve. I think that's it. So do you want to go on to the conclusion here, and we'll call it a day?
Can do. Let's see. Thanks, Steve. So just a couple more concluding slides here. We do have some information there. This recording will be posted on YouTube. There's a really quick turnaround there. So if you're interested in the content that we have there, just hang tight, and you should see it up on YouTube. Like honestly, probably tomorrow, maybe even day after tomorrow. And thanks for attending, and really appreciate the questions and the discussions that we had, and hope to see you in a future class. And that's it. Thanks, everyone.
Thank you, everybody.